The second method we will introduce to solve particular solution is called matrix diagonalization. So matrix diagonalization. And remind you what is the conditions to use matrix diagonalization is that this forcing function has to be constructed with constant coefficients. At the same time, this forcing function can use any general function. It doesn't has to be simple function like what we are using for the undetermined coefficients. Okay, so it's constant coefficient. At the same time, it can be arbitrary or any forcing function. Okay, and let's see how this matrix diagonalization works. So you have a system you are trying to solve is y prime equals to ay plus g, which the g is the forcing function. You can already solve the homogeneous solution without the g part. So when g is equals to 0, then the y prime equals to ay will give you the homogeneous solution, where this homogeneous solution will look like x1, x2, dot, 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 to xn, n times c1 e to the lambda 1t, c2 e to the lambda 2t, dot, 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 cn e to the lambda nt, where this part is your model matrix constructed by all the eigenvectors. This part, lambda 1 to lambda n, is your eigenvalues. Okay, so we can also write as a model matrix represented by T times Z, where we represent this C1 e to the lambda 1 to Cn e to the lambda n. Okay, then for the matrix diagonalization, we assume that y in general, so this is the general solution, y is equals to tz. Okay, so in general, we assume general solution y is equals to tz. Then what you can get y prime, okay, y prime will be equals to tz prime will be equals to the z prime will be equals to a y plus g, and this y is equals to tz. Tz will be a tz plus g, so that you can get this part and this part should be equals to each other. So tz prime equals to a tz plus g. Okay, so that is the equations we derive from y prime. Then after that, we can just times multiply the t inverse on both left and the right, so that we only left z prime equals to t inverse at z plus g. Okay, oh, t inverse g. You have to times both the t inverse on the left and the right. Then t is what? T inverse AT is a diagonal matrix we already proved before. dz plus t inverse g. This diagonal matrix, what is the diagonal values? They are all the eigenvalues there, right? So T inverse AT equals to a diagonal matrix where the diagonal elements are all the eigenvalues, T inverse G. Then we can write our equations. Z prime will be equals to dz plus some function where this function h is equals to T inverse G. Okay, and we can write, for example, for each component inside this z, which zi prime will be equals to. So each component in the d part will be lambda. Okay, so lambda I zi plus hi. That is using linear algebra equations to represent this functions, to represent these matrices. Then you can get this zi prime minus lambda I zi minus hi equals to 0. So you can see this become linear ODE, first order linear ODE for zi. Okay, and we know how to solve this linear ODE since the beginning of our lectures. Okay, so our ZIT is equals to e to the lambda it times integral e to the negative lambda it times hit dt plus ci. This ci is some arbitrary constant. Okay. Then you can basically solve the z. You can get what is uy because the y is represented by the model matrices times the z. Okay. And here something to note is if you leave the ci out from the previous equations here, then you will get the particular solution. Well, if you with the combination of with combined ci, then it will be your general solution, which include both your homogeneous equation solutions as well as your particular solutions. Okay. So this is our matrix diagonalization, and we will make examples using matrix diagonalization to solve our general solution of the higher order ODE.